Hello, class, and welcome to lesson 6.1. It's the first lesson in Unit 6. Unit 6 is called Normal Distribution. So we're going to be tying in mostly data from continuous situations, but we're also going to learn how do we incorporate that discrete data into this as well. In order to do most of this unit, folks, you're going to learn that in order to calculate the probability in normal distribution, it's the area under the graph. So you're going to see that we're going to do a lot of graphing in this unit of different types of functions so that we can then calculate the probability under it. Okay, so we're going to start with graphing exponential functions. Remember, if we have exponential growth, it increases from left to right. And if it's a growth, the base is greater than 1. If we have a decay, which means it comes down or decreases as we go from left to right, okay, that is a decrease or a decay is another word that we call it, and the base is between 0 and 1. All right. Now, some of this stuff we'll review, but there's going to be some new points we're throwing in at you as well. So I want you to graph 4 different things, A, B, C, D, and you're probably like, okay, Miss R, I recognize A, I recognize C kind of, or maybe D, but B is quite new. Okay, and I'm going to explain about that right here. I would also recommend, because there's a lot of mathematical work here, if you haven't printed off the answer key, you might want to print it off, or just realize that it's going to take you a while to fill in a lot of the data for this one. We just want to catch you up to make sure that you're ready to rock and roll. You'll notice that for many of these examples in this lesson, I've kept the answers in the tables just to simply save time. Okay, please feel free at any time to pause my video to get the answers written down. Okay, all right, so I apologize for going the answers, but it's just going to save you time. All right, so let's take a look at this E. E is a special irrational number, and it's equivalent to almost that. And the reason why it says ... is because irrational numbers do not terminate, means they don't end, and they don't have a repeating decimal pattern. So that's what makes them irrational. Another example like that is pi, right? So 3.14 ... keeps going, right? Okay? And this is used in math and science. And it's the base of the natural system of logarithms. If you can just throw of in there, I missed that word. Okay, and so if you look on your calculator, there's a special button for it. Okay, it's probably going to be e to the x. Okay, so take a look, find that button. It might be a shift of the ln button, ln. Okay. All right, now it says to graph each of these. So I've set up 4 table of values, okay? And if you forget how to do this, ladies and gentlemen, I'll kind of go over one example. So if we want to find the y value at x is -3, we're going to sub in wherever we see an x, we're going to put a -3. Remember, ladies and gentlemen, that's a negative exponent, so to make it positive, it's 1/2 to the +3. And then remember that 2 cubed is 8. So you have a final answer of 1/8. And then if some people like decimal form, that's what the calculator will give you if you just plug it in right away. So you can just take your calculator, plug that in to either y to the x or hat -3, and you'll get that decimal answer. All right, so taking a look at the first graph, ladies and gentlemen, in red, it's y equals 2 to the x. Okay, and notice that it's a growth, so as we go from left to right, it increases because the base is greater than 1. Also remember, folks, for exponential functions that we have what's called an asymptote. It is a line that a curve gets closer and closer to but will never touch or cross. Okay, if you're not sure about what that is, take a look at that. It helps you with graphing. Okay. All right, now the next one, folks, is this E. Okay, so E is around 2.7. Okay, so it's a bit bigger than this base. So again, plug it in your calculator. So you're going to go E for the first one. You're going to go E to the -3, plug it in, it'll give you a value. Okay, hopefully you get 0.0498. If you're not getting these values, please come see me in class and I'll go over it with you on your calculator. Okay, so plug those in, and notice for our second graph here on the graph, it's a little higher because the base is a little larger. Okay, again, it still has that asymptotic behavior as well. Okay, because although it's an e function, it is still an exponential because the exponent is still the value, is still the x when you think about it. Awesome. Okay, let's keep going. Now let's take a look at what's happening here. Okay, so now we've got a little bit of some complication here. So normally I say if the base is negative, then, if the base is between 0 and 1, then we have a decay. But now we're dealing with negative exponents. So when you have a negative exponent, you have to graph it to see what happens. Okay, so if we did 5 to the negative x, we plug it in, and notice this time it's a little switch. So when I do this, okay, if I go 5 to the negative times negative 3, negative times a negative gives you a positive, so it's going to be 5 to the positive 3, which then equals 125, if you're wondering where that's coming from. Okay, all right, so taking a look at your trends, this becomes a decay function. Okay, this may be new because I don't think we dealt with exponentials with negatives in grade 11. Okay, so this might be a newer approach. Okay, so then we take a look at the third graph, and when we graph it, we notice that most of the data, the higher numbers we can't fit on. Okay, but it starts high, goes low again. It has that asymptotic behavior. Okay, now let's take a look at the fourth graph. The fourth graph is a little bit harder when you do your substitution. So if I take a look at this first one, it's going to be y equals 10 to the negative 2 times negative 3. Negative times negative gives you a positive, and 2 times 3 is 6. So that's what gives you 10 to the 6. And so how do I do this? Ladies and gentlemen, I know I've got 6 zeros, so I write a 1 and then I write 6 zeros. 1, 2, 3, 1, 2, 3. That gives you 1 million. Okay? That's a trick. You actually don't even need a calculator when you're doing that. All right. So taking a look at that graph again, because the exponent is negative 2x, it's a bigger exponent. That means it's a steeper decay. All right. Cool. So again, this is just one type of function we're going to be taking a look at throughout the unit. We'll be taking a look at others. All right. Now we're going to take a look at how we graph the probability frequency. My fault. My brain was turned off there for a second. Okay. So remember, when we're taking a look at graphing it, we are going to take a look at the relative frequency, because in order to create the graph, you have to have the relative frequency. So let's take a look at an example here of fruit flies. Boy, oh boy, don't have fruit flies in your locker. Okay. We monitored so we took a look at 1,000 fruit flies, and they were monitored for their lifespan. Results are given. Okay, graph the relative frequency diagram. Okay, so in order to graph it, you have to do a table. So you're going to take a look at our table here, which the values are given here. Okay, but remember, in order to take a look at graphing it, you need to do what's called the relative frequency. Okay, because that's what it asked for. All right, so remember, in order to take a look, for example, 0 to 4, we had 480 out of a total of how many fruit flies? So what does that mean, folks? That 48% of the fruit flies lived 0 to 4 days. Okay, how many lived 4 to 8? 26%. All right, etc., etc. So once you have, ladies and gentlemen, once you have your relative frequencies done for all of them, the same pattern would apply. You take the number and divide by 1,000. Okay, then to graph it, you do these nice little bars because they are interval data, right? Okay, and then just ignore the area 1 and area 2 for now, or that dashed line for now, because that's going to apply to a different question. So just imagine the black bars right now. Okay, all right, awesome. Okay, so now it says to estimate the probability that a fruit fly lives 6 days or less. And that's when I take a look at the graph. And if I have 6 days or less, notice 6 days is halfway between 4 and 8, and that's why I've got that colored in blue diagram. Okay, and what we're going to learn in this unit is that, I think I mentioned already, but probability, when we take a look at normal distribution, is going to be the area under the graph. Okay, and it's going to be the shaded area. I just put that in brackets. So area under the graph, and it's the shaded area we're looking for. Okay, and we'll be using the graphing calculators, and the graphing calculators will shade it for us too eventually, but we're going to learn how to do it by hand as well. All right, so what we need to figure out, folks, and watch your terminology. I know in your last unit test, a lot of people were missing this terminology, so let's make sure we had it. So, probability when x is less than or equal to 6 is the combination of the area 1 plus the area 2. Okay. All right, so area 1, it's a full bar, right? So we're going to say area 1 equals 1 times 0.48, okay? Plus, now taking a look at the second area, it's only half. So it's going to be 1/2 times 0.26, because it's only half of the whole bar. Okay, plug that in your calculator, folks, and you're going to get 0.61. So what does that tell us? That we have a 61% chance that a fruit fly will live 6 days or less. Okay, eventually, ladies and gentlemen, we are going to take a look at, if I was to graph this, and you're like, well, Miss Howard, this is just a bar diagram. How do I make it exponential? Well, if I take a look at all of the midpoints that occur, okay, and I draw a smooth curve between it, and we're going to getting this into this later on in the unit. Okay, we'll be dealing with areas like this. And you say, hey, Miss R, how do we figure this out? Well, when you take a look at this area that's extra kind of matches this area that that is outside. So those kind of overlap. So we're going to be taking a look at cases with that a little later on in the unit, just letting you know that graphing is going to be a big part of this, and so is the shading. All right, let's keep moving on, folks. Okay, so if we know that type of distribution the data has, we can do theoretical probability under the calculations by finding the area under the curve. So this is a thing to make sure you know, put a star around it. To find the theoretical probability, it's the area under the curve. All right. But sometimes it's hard to do the area under the curve. And let's take a look at this this example 3 as to why. Okay, so it says, give the probability distribution for x, where x is the number of times you roll an even number in 5 rolls of a fair 6-sided die. Okay, so remember, fair means that it's not weighted on one side. Okay, don't forget there's many different types of die. So if you want to see, ask me. I have like a 12-sided die. I think I have a 30-sided die. I have a die inside of a die. Just ask me and I'll show you my different dice. It's kind of cool. But anyway, let's get back to this problem. I'm off on a tangent, sorry. Okay, so let's take a look at how do we calculate this. Well, what does x represent? What are we looking for? X is the number of even rolls. So number of even numbered rolls. Well, when we roll a die, what are the even numbers? Okay, well, they are 2, 4, and 6, when we think about it, right? Okay, so what's the probability of getting even numbers? Well, that's 3 out of 6 possibilities, so P equals 0.5. We take a look at Q, which is the opposite, which is the odd. Okay, odd numbers rolls is 1, 3, and 5. And again, what's the probability of that? Probability equals 0.5 for the fail. So I apologize, I'm going to get rid of the brackets and put equal sign down here. There we go. All right, so in order to do this, folks, we want to know the number of even rolls. So we can have x be 0, which means we have 0 even rolls, which means they're all failures, right? Okay, next we can do 1 even number, 2, 3, 4, 5, and you'll see why I left this data on here, because it's probably easier. But remember, folks, can you have something like 1.5 or 3.5? You can't. So that we remember, this is still discrete data. Okay, so when we go to graph this, we have our probability of even rolls. That's our title there, if you're wondering where it is. Okay, we set it up, and again, because it's discrete data, we can't calculate the area. But don't worry, folks. I'm just giving you a little bit of a cliffhanger here. We will learn how to deal with discrete data in lesson 6.8, and it's called the continuity correction. So we can get approximate values, but we can't get completely accurate. Okay? All right. One last thing I want to bring to your attention that's going to play out in this unit a lot is called Z-scores. Now, this was something that when you look for your formula sheet, folks, for example, if you look for the Z-score formula, which are these two right here, you're going to find them in with the stats unit at the beginning. So on your formula sheet, look at the beginning, and you'll find Z-scores. Okay? And what does Z-scores mean? It's the measure of the standard deviations of a datum above or below the mean. So how far is something above or below the mean? Okay, we'll take a look at percentiles in this course. We'll take a look at SAT scores, dealing with that. And quite often when universities in the States, you have to take SATs. In order to get into a certain university, you have to have a certain percentile, which is related to your Z-score. How far away are you from the average? Okay. All right, so just remember there's two different formulas, so let's just go over the terminology here. The mu, folks, which is your funny looking U, okay, that represents the mean, okay, and that's when you've got a population, okay, where you do the census like I had to do the other day, okay. Whereas if you just have a sample, ladies, another one, folks, is the other sign for that is the X bar. If you have a sample, right? Okay, taking a look at standard deviation, you're going to have your sigma, and that represents standard deviation. Is everybody okay with that? All right, and I'll just write that down in a second. I'm sorry, I'm just trying to find the other symbol, which is just S. I was double checking. That was just S. Okay, so S if it's a sample, but the sigma because, sorry, yes, the sigma because it is a population. So this represents standard deviation. You might say, hey, Ms. R, why didn't we learn this in Unit 1? Well, it ties in better with what we're going to do with it because we're going to relate it to probability, so that's why I save it for now. Okay? You can tell me later on if you think that's a good idea or we should have learned it ahead. I would love your opinion. All right, so what we need to do is remember that for each formula, because it's how far the standard deviation is from the mean and standard deviation is in each question, okay, related to a data point. Okay, so it says to find the data scores for 43 and 76. Okay, so let's do 43 first. Okay, so you take the data point, which is just the X, okay, subtract the mean and divide by the standard deviation, okay, and that gives you negative 1.85. Okay, so I need you to write this down. This means that 43 is 1.83 standard deviations below the mean. It's below the mean because it's negative. Okay, there's a negative sign there. That's important, and that's because it's negative. So it's below average. Okay. If you want to pretend like that we've got class marks, folks, and my mean in the class is 72%. Okay, and my standard deviation is 16. Okay, if someone's sitting with a 43, guess what? They're not doing so well. So that's why they're below the mean or below the average. Okay, let's take a look at another example. So say you've got a mark of 76 in the class. Okay, and say that the mean is 72.8. So you take your mark, subtract 72.8, divided by my standard deviation, and that means 0.2. So this means that 76, the mark of 76, is 0.2 standard deviations above the mean. It's above because it is positive here, right? Okay. All right, so we're almost done, folks, and the thing I want you to write down here is we will relate Z-scores to probability in future lessons. If you want a sneak peek, take a look at page 606 and 607. Okay, you can quickly turn to that in your textbook, ladies and gentlemen. Okay, let's see if we can do this. So take a look at that, and ladies and gentlemen, I will provide you this on your next unit test, this sheet, as well as on your final exam. Okay, so you will notice that we're taking a look at normal distribution. It's the area under the curve. So take a look. One side is positive and one side is negative, and you got to match it up. So your first two decimals always go down first and then across. Okay, so for the first one, which was negative 1.83, got to be on the negative side, go to 1.8 on the left column, and scoot down until you get to the 3, and then that tells you the probability. So what does that mean, folks? That means you have a 3.2% chance to have that mark in the class. So that's the probability. Okay, look at the second example. Try and line this up, folks. Sorry, just give me a second. 0.2. So you got to go 0.200. Okay. Okay. And looking at that, folks, that means you've got a 50, I think it's a 58% chance. I'm going to double check that, but I think it's a 58% chance of having a mark of that in the class. All right, so that's coming later on, but I just wanted to make sure you've got it. So, ladies and gentlemen, here is your homework. Page 412, numbers 1 to 3, 8 and 9. Use a graphing calculator when needed, and please make sure to ask for one if you need it. Have a great day, folks, and of course, come see me if you need any help. Ciao.